So now that we can solve systems of equations relatively painlessly, I want to revisit something that we talked about earlier, which is that um, when we have a system of equations, the possible solutions are a unique solution, no solution, or an infinite number of solutions. Now, there's not much to say about systems with no solutions, but in a system with, let's say, infinitely many solutions, you can still describe those solutions in some meaningful way. And so what we're going to do in this video is we're going to talk about when to recognize uh, when a system has no or infinitely many solutions, and what to do, if anything, in such a scenario. So here we have a system of equations: 2x plus y plus z is 3, x plus z is 4, 0y, 4x plus y plus 3z is 11. And so what we want then is to uh, write this as an augmented matrix. So 2, 1, 4, 1, 0, 1, 1, 1, 3, 3, 4, 11. And we're going to find the reduced row echelon form. And when we do, we're going to see why something goes differently this time compared to previous situations. But I'm going to go back to the Sage cell we had before. I'm going to go ahead and enter in the new information that we have. So we have 2, 1, 1, 3, 1, 0, 1, 4, and the last row is 4, 1, 3, 11. Right? Those are the three rows corresponding to our three equations, right? So now when I go ahead and evaluate this, well, there's my non-reduced row echelon matrix, as we saw before, and this is what happens afterwards. So notice that I don't get a variable in this last row, right? I just get 0, 0, 0, 0. And instead, I have entries here in the last row for this last equation. So let's talk about what's happening here geometrically. What's happening here is each one of these equations represents a plane. So I have a plane and I have another plane that intersects it. And the third plane is actually coming in and intersecting where the two original planes had already intersected, meaning that it's not narrowing down the solution set by anything. It's not coming in like this and narrowing it down to one point. So what we have here are three planes that are all intersecting at the same line. And that means we're in a situation with infinitely many solutions. Now, just because we have infinitely many solutions doesn't mean that we know absolutely nothing about what's going on here. We know that these three planes do intersect at a line, and we should be able to then give some sort of description of what that line might look like. And so what I'm going to do here is I'm going to write down our reduced row echelon matrix: 1, 0, 0, 0, 1, 0, 1, negative 1, 0, 4, negative 5, 0. And let's go back to our whiteboard, or whatever you want to call this. So that's our reduced row echelon matrix. If I rewrite these two equations now as a system of equations, what I have is that x plus z is equal to 4, and y minus z is equal to negative 5. And then the last equation says that 0 is equal to 0, which is useless, but true, I guess, but not helpful to us in any way, right? So I can rewrite both of these equations to be something like x is minus z plus 4 and y is z minus 5. And so what that does is it says, all right, there's 3 variables that correspond to our 3-dimensional space, but they all intersect at some line, right? At some line in the space. And if I told you the z variable at some point, I could tell you both the x and the y values, both the x and the y of that point. So, whereas I can't narrow it down to one solution, I could look at this and say, well, if I told you, if I knew what x or y or z was, I could tell you what the other 2 variables are. Just like in 2-dimensional space, if you have a y equals mx plus b line, if you knew what x was, that'll tell you what y is. If you knew what y was, that'll tell you what x was. So for example, if, right, if it just so happened to be that x were 3, this equation would tell us that z had to be negative 1, right, in order for x to be 3. And if z were negative 1, then y would be negative 6, right? So given that x is 3, you could deduce the other 2. If you knew that, say, z were 4, you could deduce that x were 0 and that y were negative 1, right? So everything can, the other 2 variables are totally determined by what any one of them does, and that's the characterization of a one-dimensional space. And so if let's just pick a variable z, if I knew what z was doing, I knew exactly what x and y were doing. So my solutions here are all of the form, the x value is minus z plus 4, the y values are z minus 5, and the z values are just z, right? So that's the general form for my solutions here. Alright, so let's do another example of there not being a unique solution. Let's say that my system of equations were to be something like this. I'm going to skip out writing the actual system. So if x plus y plus 2z is 3, minus x plus 2y plus z is 1, 3y plus 3z is negative 5. Alright, so let's go ahead and put that in our Sage. So our first row is 1, 1, 2, 3. The second row is going to be negative 1, 2, 1, 1. The third row is 0, 3, 3, negative 5. Pop that through, bloop. And I have this augmented matrix here, which I'm going to write out. First row is 1, 0, 1, 0. Second row is 0, 1, 1, 0. And the last row is very curiously 0, 0, 1, 0, 0, 0, 1. Alright, so that's the reduced row echelon form of this original matrix. Let's go back to whiteboard, and here I've written it down. Now this time I will write what the system is because it's very instructive if we can see it. In the first row, what we observe is x plus z is 0, right? In the second row, what we have is y plus z is 0. And in the third row, and this is the important row, 0x plus 0y plus 0z is 1. Now this should bother you because 0x is 0, 0y is 0, and 0z is 0. So the left hand side is 0, 0, 0. And the right hand side is 1. So in order for this solution to be solvable, for the system to be solvable, you need an x, y, and z so that 0 is equal to 1. Well, there's no such thing, right? Clearly. So there is no solution, right? That it's impossible to find any x, y, z. It doesn't matter who you pick. 0 is never going to be equal to 1. So this is a big ol' no solutions. Right? And so the key thing to remember is that in each case, our reduced row echelon matrix represents a system of equations. Sometimes the system of equations boils down to something that is that doesn't give a unique solution, but that you can find a general form for that solution. And sometimes that system of equations gives you an equation that indicates it can't be solved. So, of course, what both of these situations have in common is this 0 row. Right? So in a 3 by 3 or an n by n situation, seeing that 0 row is a sign that something is not awry, but that you're not looking at a unique solution anymore. Because what it's telling you, putting that 0 in the last row, is that, oh, you don't have a solution for z. Well, if you don't have a solution, a specific solution for z, that's either because z could be anything, or z can't be anything. Either way, you're looking at infinitely many or no solutions. Alright. Hopefully that was helpful. Thank you very much for watching. If you have any questions, please let me know, and I will see you in the next video.